Brilliant. Okay. Good afternoon, everyone. I hope you didn't just get out of bed, although I can pretty much guarantee that some of you just did. We're going to talk about defects in our solids today, right? We're going to mainly focus on crystalline solids to start with, and we'll touch on our amorphous solids. I hope these words mean something to you now. And then finally, we'll look at our polymeric solids. And we'll look at something called an hysteresis loop. Okay, so a bit of reading to start with, right, just to get us in the groove. If you just follow with me here, it says a perfect crystal with every atom of the same type in the correct position does not exist. Now, how interesting is that, right? So think of the of diamonds. I'm sure you know about the carat of diamonds and the clarity of a diamond. That's measured on its defects, okay? The things that are wrong with it. And it says all crystals have some defects. And these defects contribute to the properties of the metal, such as its melting point or breaking stress, etc. And then it says, using the term defect is a sort of misnomer, since these features are commonly intentionally used to manipulate the properties of the material. Okay, so engineers will put defects into certain materials to make it have certain properties, right? And when you put two materials together, of course, especially metals, that's called an alloy. And that will very much affect its stretchiness, bendiness, melting point, etc. Okay. However, even though we don't like the word defect, as in something wrong with it, but that's what we call them in physics, a defect. But it's not always a bad thing. And for our crystalline solids, there are three types that you need to be aware of: a point defect, a linear defect, and a planar defect. Okay, so a point defect is a place where a single atom is missing or irregularly placed, right, in the lattice structure. So think of your lattice structure in the crystalline solid, just that nice regular lattice. Well, if you take one out or put an extra one in, that's called a point defect. A linear defect is where groups of these atoms are in irregular positions. And the linear defect is commonly called a dislocation, which we will talk about in much more depth very shortly. And then a planar defect is what we discussed last time at a grade boundary, right? So picture a piece of glass and all my atoms on the left are in one structure, but then there's a line there and all my atoms on the right are in another structure, and that's called a grain boundary. And that's a planar defect, so like two planes of atoms meeting where a defect occurs, right? Okay, so they're things you're just going to have to learn off by heart. And then we talk about deformation, and we've mentioned this now in this topic a few times. So if you apply a load to something, whatever it is, it will stretch. Okay, brittle materials like glass don't stretch very much at all, and we'll find out why in a moment. And they just go straight to breaking point. But something plastic, like a Tesco's carrier bag, other carrier bags are available. You can stretch that a little bit and let go, and it'll go back to its normal original structure. You can stretch it a bit more, and before it actually breaks, you will damage the molecular structure, let go, and it won't go back to its original structure. Now, if it does go back to the original structure, it's called an elastic deformation. And that, as you can see there highlighted, that involves stretching the bonds between the atoms, but they don't move or slip past each other. However, if you reach that elastic limit and stretch that bag so when you let it go, it doesn't go back to its original form, that's called a plastic deformation. And it does involve breaking a certain number of atomic bonds, okay, by movement of a dislocation, which I'm going to show you very shortly. Right, so turn it over the page, okay? Right. What I need us to focus on is this diagram here. And the caterpillar, yes, you are looking at the right thing, and the caterpillar underneath. Now, this is a almost guaranteed to come up exam style question. It'll be on your homework today. It'll be on the test you have on this unit. And if you ever do sit an exam ever again in your life, it'll probably be on that as well, right? So look at this lattice structure of atoms in front of you. And you can see there's a slight irregularity there, okay? I've got, a row of 7, a row of 7, a row of 7, but in the middle here, I've got a row of 3 that doesn't seem to be bonded to the rest of them. A row of 7, a row of 7, and a row of 7, okay? So there's my impurity, these 3 atoms here. Now, let's just read through it. The edge defect, that's this, can be easily visualized as an extra half plane of atoms in a lattice, right? So I've got half a row stuck on its own in the middle. The dislocation is called a line defect because the locus, so that's the pattern of movement that you would have done in mathematics, the locus of defective points produced in the lattice by the dislocation lie along a line. This line runs along the top of the extra half plane. The interatomic bonds are significantly distorted only in the immediate vicinity of the dislocation line. Right, so for some of you, it might be a bit early in the day to have that thrown at you. So let's talk about it in more detail. This line here, this sentence here, you need to highlight, okay? Understanding the movement of a dislocation is key to understanding why dislocations allow deformation to occur at much lower stress than in a perfect crystal. So what that means in layman's terms is, if we have a dislocation like this, we can bend or move or stretch or even break this particular piece of material with a much smaller force than if it wasn't there, okay? So imagine I'm applying a force left to right as we are looking at here. Let's talk about what happens to these 3 dodgy atoms that are not in the regular lattice. And it's much like a caterpillar effect, okay? So this motion of this dislocation is analogous to movement of a caterpillar. So you've all seen a caterpillar, and it doesn't just slide along the ground, right? You see a hump of it moving along its body. Right? It says the caterpillar would have to exert a large force to move its entire body at once. Instead, it moves the rear portion forward a small amount at a time, creating the hump that we see, and that's how the whole thing moves forward. And that's exactly what goes on with these dislocations, right? If I exert some force on the left of this material, from left to right, this dislocation will move over 1 notch. And now the broken bonds would be here on the next row. And then the dislocation would move over a notch again. And the broken bonds would have moved over as well. And so on, until the dislocation atoms actually end up sticking out on the end, right? And there is your deformation. Now, on a macroscopic scale, on a real life scale, this material has actually changed shape. Just quickly go through that again, because that's a big concept and we'll revisit it a few times. Here's my impurity. As I apply force to it, it will move through the lattice. Right? It won't create or form any new bonds. It moves them over. And eventually, as that moves, it will stick out on the end. And of course, you will have a different physical shape. And that is how this concept of dislocations works, okay? And we'll go through it again. It's quite a toughy thing to understand. But on an exam, you will need to replicate a diagram like this or diagrams like these, showing how these impurities will move over and end up altering the shape of the material, which of course we refer to as a deformation. Okay, now I'm not going to keep saying any questions because I know none of you will speak. If you definitely want to say something or have a question, just raise your hand or type it in or say something and I will. But I'm not just going to keep asking, right? Okay. Let's just read this top paragraph here. As shown in the set of images that we just spoke about, the dislocation moves at a small amount at a time. The dislocation in the top half of the crystal is slipping 1 plane at a time as it moves to the right. from the left. In the process of slipping one plane at a time, the dislocation propagates across the crystal. Just a posh way of saying it's moving. The movement of the dislocation across the plane eventually causes the top half of the crystal to move with respect to the bottom half. However, only a small fraction of the bonds are broken at any given time. Movement in this manner requires a much smaller force than breaking all the bonds across the middle plane at the same time. Okay, so you can bend something or stretch something or change the shape of something with a much lower force if it has these impurities called a dislocation, rather than just moving the whole plane of atoms. Okay, so I'm hoping that makes some sort of sense, and we'll revisit it lots. We spoke about grain boundaries in amorphous solids before, so I'm not going to focus on that. I put a red across there. You don't really need it, but in a nutshell, here's a plane of glass. I've got a very tight, regular structure of atoms there and there, but there's a grain boundary here, and that, which we'll come on to later, is a weak point, which is where the glass would break. Okay, right, moving on. A few more definitions that we have met before. They're on the front page of the first booklet in this unit. But let's talk about them in a bit more detail. You will need to know these words. You will need to know the definition of malleable and ductile. Okay, you need to know that. And you're also going to need to know why now on a molecular level they occur. So metals are essentially described as malleable because it means they can be, it says you're beaten, it's a bit extreme, it can be beaten into sheets. So they can be, drawn out, thinned out, stretched, bent, all of those things before they break, okay? So malleable means that it can be bent and shaped, and ductile means it can be drawn out into a wire. Just learn that off by heart. Ductile means drawn out into a wire. So if I had, it's just a bar of metal and I was strong enough, if I pulled it and pulled it, it's like glue tack in some sort of way, it would stretch out, it would thin out, and it would become a wire, right? And that's what we mean by ductile. Malleable means if I hit it with a hammer, it'll bend, and I can shape it to how I want it. And this is because of the lattice structure of the atoms in the metal, right? The ability of the atoms to roll over each other into new positions without breaking the metallic bond. So think of your lattice structure of atoms here, and these layers of atoms can roll over each other and then slot into the new gap accordingly, okay? And they'll always fall back into the right place. If a small stress is put onto the metal, the layers of atoms will start to roll over each other. If the stress is released again, they'll fall back into their original slot. This is where it's said to be elastic, right? So it goes back to its original form. That deformation is elastic. However, if a larger stress is put on the atoms, they'll roll over each other and fall into a new slot. And that's where the permanent change of shape occurs, right? Okay. Something else about metals that you will have known. I'm sure you've all seen footage of a blacksmith, in some history program, and they always have a metal rod in the fire before they start hammering it to shape it into the sword or whatever they're making. And that's called heat treatment or work in the metal. And it's reasonably common sense. If the metal is cold, the bonds are much stronger and less malleable. But if you heat up the metal, you break some of the regular arrangements of those atoms, and then it's much easier to manipulate and hence become malleable, right? And that's called working the metal. So you might want to highlight that, and you might get an exam question like, why does heating up a metal result in being more malleable? And there's the reason why, okay? Heating a metal, the atoms will move around more in the lattice. Right, I know I'm going fast, I hope you're still with me. couple of other new words now. I want to talk about creep and necking. Okay, they have other meanings as well. Ductile. Okay, so metals like copper are ductile. They can be drawn into a wire. That is all I want you to remember. And this happens because the atoms move as the dislocations in the crystal structure move to places of lower stress. The metal will become thinner when the atoms move away from the stressed part. However, this causes the stress to increase because the cross-sectional area is now decreased. Don't forget, stress is force divided by area. So when you're thinning it out, the cross-sectional area decreases, and because you're dividing by that, it means the stress will increase. Okay, so there's the mathematics behind that. This further increases the ductile flow, the stretching out of it, and so the metal yields and gets thinner and thinner. So yields means sort of gives way on an atomic level. You shouldn't be able to grab a piece of metal and pull it and stretch it, but that is why it happens, right? And that's called yielding. And once plastic deformation starts, think of that graph that we spoke about last time, once you hit that point of no return, you'll need less and less stress for it to continue to stretch, until, of course, it will eventually break. Okay? The stretching under a constant load is called creep. Don't need to worry about that. But the thinning of the rod is called necking. And this one I have seen come up. What do we mean by necking, right? So it's applying a stress to a metal rod, copper wire, and as you start to stretch it, its cross-sectional area decreases, which means the stress will increase. It'll keep stretching, it becomes thinner, 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 and that's called necking. Okay? So there's a couple of words and definitions there that are brand new, and you're probably thinking, wow, why did I take physics? Hang in there. Right. On to the next one. So that enough for the time being on crystalline solids. Let's have a little talk about amorphous solids. Of course, that's brittle stuff. So glass, china, we normally use glass, right? Those are all examples. Here's our stress strain graph for a brittle solid. Okay, there's no curve there. There's no elastic limit. It doesn't then stretch a bit and yield. It just follows Hooke's law for a bit and then snaps. Okay. They cannot flow, so they do not neck. So don't forget, necking is the thinning out. And here's why. The fracture in a brittle material like glass is due to something called a crack, okay, and crack propagation. If a brittle material is placed under tension, basically it's been stretched or pulled or has a weight on it, some bonds will break and a crack will start to form. So look at this very crude diagram here. There's a bond missing there and a bond missing there. So here is the formation of the crack. This will then increase the stress on the remaining bonds. So now there's more pressure and stress on these, and that crack will start to propagate throughout the amorphous solid, which will in turn cause them to be more likely to fail, which just means the bonds are broken and it breaks in two. Okay. Now, what's interesting with brittle materials is compression, which is obviously the opposite to extension. So let's think of a glass rod here. If there was a slight crack in it here, right, a slight molecular defect here, and I bent it that way, it would just immediately break. However, if I flipped it up the other way, so the crack was on the bottom, and I bent it almost inwards, it would actually become very strong there because you are closing up the gap in the molecular bonds, right? You're closing up that, I have to say it, crack, right? So that's really interesting how compression will strengthen a brittle material. Now you'll see that later. You'll see it a lot in real life. In fact, don't you turn over the pages yet. I would like to get there myself. And that is why, right, if you look at a lot of old historic buildings, they all have arches, right? And that's because this arch construction structure uses compression forces to keep that in place, right? So we'll talk about that more later. Right, back to where we were. Where were we? Did that. Right. So you're going to see this graph a million times. You need to know this graph. Here's the stress strain graph for glass, straight line, Hooke's law, brakes. Here's the stress strain graph for copper, for example. Hooke's law, you reach an elastic limit, then it starts to yield, then it will neck and stretch, and then it eventually breaks. Right? And don't forget, if we let it go at some point around here, it would actually return back not to its original state, but close to it. Okay, and we'll talk about that more in a moment. Right, don't need the rest of that page, so let's turn over. So, right, my answers are on there. Right, so I'm going to change to here. All right, so I have some questions for you to try. Just give you a couple of minutes. Right, so straight off an exam paper. Here, hopefully you can see the stress strain curves for 3 types of steel. Okay, so we have what's called a quenched alloy steel, a high carbon steel, and a low carbon steel. So I'd just like you to have a little think about for 30 seconds, which is the most ductile, right? So which one can be drawn out into a wire the easiest? Which has the highest break-in stress? So which one will need the most force for it to actually break? And what can you say about the Young's modulus for each of them? Okay, and don't forget Young's modulus is stress divided by strain. So have a little think just for 30 seconds about those 3 questions there. Obviously, I'll give you the answers in a moment. Just have a little think. Right. So, which is, oh, it does say to give reasons. Which is the most ductile? So the most ductile is the low carbon steel. As you can see here, it reaches its elastic limit first. It has the lowest yield point and the lowest break-in point as well, right? So basically, that's the stretchiest, which isn't the best term to use, right? But that's why low carbon is the most ductile. Which has the highest break-in stress? Well, it breaks at the end of the graphs, so it breaks here, here, and here. Obviously, this one here is the highest one, the quenched alloy. And what can you say about the Young's modulus for each, right? And don't forget, the Young's modulus is the stress divided by strain. So up until this point here, they all had exactly the same Young's modulus. So whilst they were all obeying Hooke's law, the Young's modulus was the same. So it's equal up to a point, then the alloy content causes differences, right? The amount of carbon being put into it is different. So that's what produces the difference in the Young's modulus for each type of steel, okay? After this point, the quenched alloy has the highest Young's modulus, then the high carbon, and then the low carbon. I'm hoping, now I've gone through it, you go, oh yeah, I can see that now. I understand what the words ductile mean, the breaking stress, etc. Right, brilliant. So, next one. So you are going to do this now. 6 marks for this, right? 6 marks. Sketch a typical stress strain graph for the stretching to breaking point of a ductile metal such as copper, right? So you know what the shape of this is going to be. It's going to go up there and then down there and then up a little bit like that. Just like the ones we just looked at on the last question for steel. Label on it the elastic limit, the yield point, the region of plastic deformation, and the breaking point. So I need those 4 things clearly labeled, right? So don't just sit there now doing nothing. On your pack, get a pencil, sketch it, and annotate it accordingly. All right, I'll give you another 30 odd seconds and then I'll show you what you should have. If you want, you can just write A, B, C, and D rather than write out all of the words. And the fact that this is 6 marks on an exam is amazing, because once you've learned how to do this once, it ain't going to change for any crystalline solid such as a metal. You haven't got to be Picasso about it. Okay, so here's what I've got. So there's the basic form of the graph. That's meant to be a straight line there, went a bit wobbly. Should use a ruler probably. All right, so it obeys Hooke's law, and then you get to this point here where it starts not being a straight line graph, and that is the elastic limit. Starts to curve slightly, you hit the yield point B, and then these 2 points here from C to D are what we call the region of plastic deformation. Where the graph ends is the breaking point of the material. And at this point C, you need to draw a dotted line back down to the start. And this here would be the amount of extension away from its original form. Okay, so that's a diagram that you just need to learn off by heart. Going to assume we're all cool. Right, next question. So, 3-mark question. The diagram shows the arrangement of atoms in a metal crystal in the region of a dislocation. So it's a bit smaller than the one we looked at earlier. There's not 7 atoms in each column. There's only 4. I have a dislocation of 2 here, and it's missing 2 bonds there, right? And they've labeled these atoms here A, B, C, D, E, F, G, H. Using the letters in the diagram, explain how plastic deformation takes place in ductile metals when forces are applied as shown by the arrows, right? So on the top half of it, I've got the force going from left to right, and on the bottom half of it, I've got the force going from right to left. Space is provided so that you can illustrate your answer if you wish to do so, or you may add. So effectively, you want to draw another 2 diagrams showing how A and B, the dislocation, are going to move over. They're going to move over one there, they're going to move over another one there, and eventually they'll stick out on the end. And that's what they're looking for to get the marks. Okay? So have a little think about how you would write that down. I will show you my solutions now. So this is what I've got. So here's the initial diagram, okay? This dislocation now has moved over to where C and D are. And these bonds have moved over underneath A and B, hence this diagram here. And I've done it one more time. I've moved the dislocation over again, and the gap has followed it, and these bonds come over to the left. So you can see now the dislocation is sort of stuck out on the end, hence the change in shape. So there was the diagrams they were looking for to accompany it. And the simple sentence you need is, as the force is applied, the dislocation point slides to the right until it reaches an end point and therefore creates plastic deformation. Okay, so have a good look at that, and if you didn't, have a go yourself, get that down, because it's exactly what they would want on the exam. This comes up all the time. So you're just showing how that dislocation slides over and eventually sticks out on the end. And because it's sticking out on the end, it's a change in shape. We call it a plastic deformation. Okay. Let's have a look at the bottom 2. Superalloys in the form of single crystals have recently been developed to withstand extreme conditions of temperature and pressure. All right, so we're taking a metal and we're putting in the impurities ourselves, so they can withstand extreme conditions of temperature and pressure. In, and in bold, terms of atomic structure give one reason why superalloys can withstand higher temperatures and pressures than conventional multicrystal alloys, right? So if we go back to this original gap here, let's say I'm able to, on an atomic level, fill that gap there. That's obviously going to make the structure stronger and those bonds more difficult to break, okay? So the impurity atoms, which is the alloy, will fill in the gaps in the atomic structure. Simple as that. And what's one application of a superalloy? Well, you're not going to know this, obviously, unless you've researched it, right? But because these superalloys that they've said have high strength and resistance to rusting or oxidation or being affected by extreme heat, we use them in things like jet engines, submarines, nuclear reactors, okay? So superalloys are used in those kinds of applications where you'll have extreme temperatures and pressures. Right, I hope that's okay. Oh, I'll give you time to write that down. Apologies. Right, we're not doing bad. I hope you're still awake. Moving on. Right. I think I do need to do something. Okay. So this is a question like the ones you did for me on the homework packet, right? I've got a light bar AB, there it is, and it's being suspended horizontally from two vertical wires. One is made of steel and one is made of brass, right? So they're going to have different Young's modulus because they are different materials. However, each wire is of the same length, though their cross-sectional areas are different. So even though they're of the same length, they have different thickness and hence a different cross-sectional area. It looks like the brass is thicker than the steel. When a force is applied to the center of AB, right? So when I hang a weight from the middle of AB, the wires extend by an equal amount. So the extension is equal, and the bar therefore remains horizontal. Right. Given that the Young modulus of steel is that, 2 times 10 to the 11, and the Young modulus of brass is that, show clearly that the cross-sectional area of the steel is twice the cross-sectional area of the brass. Now, not to freak out, okay? The extension is the same. The extension of steel and the extension of brass is the same. And as we know, the force being applied is the same, and we know the values of Young's modulus, we can easily show that, okay? So write down the formula for extension. And write down the formula for Young's modulus. There's a fly in my office. It's February the 2nd. I'm going to get up a sec while you write those formulas down. Unbelievable. Right, look at this. The Young's modulus for brass, remember, it was stress over strain. Stress is force over area. Strain is extension over length. And then you can combine them to get this formula here. Young's modulus is force times length divided by the area times the extension. And I call the extension delta L, the change in length. All right, we covered this last time. So the Young's modulus for brass is 1 times 10 to the 11. Forget the 10 to the 11. The Young's modulus for steel is 2 times 10 to the 11. Now the force applied is the same. The original length is the same. The extension is the same. So only thing that differs is the cross-sectional areas, right? And for that to work, for this one to be double that one, the cross-sectional area of this one must be double that one. So that's where that came from. Determine the tension in each wire when F is 100 newtons. And that comes out as 50 newtons. Okay? Right, have a look at the bottom one. Let me go back. Hence, which means let's use the results we've just figured out. So we now know that the force is 100 newtons. We have the Young's modulus. We know that the cross-sectional areas, one is double the other. Hence, calculate the extension in the steel wire when F is 100. The initial length of the wire is 2 meters, and the cross-sectional area is that, right? So you've got F, you've got L, you've got the Young's modulus, and you've got A. You've got 4 things out of the 5. So rearrange your equation accordingly and get me the extension, delta L. And think about it as well, right? It's a not very long piece of steel. It's not going to extend by much, is it? It's not going to be like 3 meters of extension. So try plowing those figures into that formula. So you've got Young's modulus is FL over A delta L. You need to rearrange that so it's delta L equals. Try and rearrange that formula, and then you just type the 4 numbers into the calculator. Right, let me show you then. I'm hoping you've done it. So if I rearrange my Young's modulus formula, I'm now going to get delta L equals force times original length divided by the area times the Young's modulus. Chuck all that in a calculator. And my calculator says 0.0018 meters. Multiply that by 1,000 to convert it to millimeters, and you get 1.8 millimeters, which sounds about right. Okay? Calculate the energy stored in the steel wire. The energy stored is half of the force times by the extension, right? Think of it as being the area under the graph, which would be a triangle. Half the base times the height. Force would be the height. Delta L extension would be the length. Half the base times the height. Half times 50 times this extension. Got to put it back into meters. Gives you 0.045 joules. I hope that's okay. I'll let you copy that down. Oh, just broke my pen. Sorry if you were still writing that down. Right, we're nearly there. We've got to talk about the hysteresis loop in a moment. Don't forget, we're doing this. We would have normally had 2 hours to do all of this. We would have took a break, so I know it's heavy going. Hang in there, okay? Right, you don't need the next page at all. You can, by all means, read through everything I've given you, right? But there's nothing on there you need to reproduce on the exam. Just wanted to quickly talk about the arch structure that I mentioned to you earlier, right? This is very, very much worth reading in your own time. You'll see a lot of arches in old buildings like cathedrals, churches, old bridges, and that's to do with that compression force that we spoke about earlier. It says the stones in the center of the arch are higher than the ones nearer the edges, so they are partly supported from underneath. The resultant forces from neighboring stones keep the stones compressed. Okay, so that can come up on an exam. Why was an arch structure used in old buildings? And here's another interesting thing as well, very relevant to our local Severn Bridge. Concrete is brittle, like stone. Concrete is just like an alloy of stone. But a concrete beam can be made stronger by reinforcing it with steel bars. The steel bars are embedded inside the concrete. Steel is very strong under tension and does not crack. If the reinforced concrete should begin to crumble underneath, the steel bars will become slightly extended and carry that stress. This stops the crack from propagating through the concrete and hence stops it breaking, right? And we use that a lot in the construction of large bridges and houses. And then another thing they speak about here, especially in bridges, is pre-stressing the concrete, which means compressing it, holding it there with the steel bars, and then when you take the compression away, it already has that force there, almost binding it together. Okay? It says modern engineering projects make extensive use of pre-stressed, reinforced concrete. And that's something you may need to regurgitate on an exam. All right? So read through that page. Make sure you have some sort of understanding of what's going on there. Right, we're pretty much on the last thing now. So we've discussed our malleable and ductile crystalline solids such as metals. We've discussed, and dislocations in them, obviously, very important. We've discussed cracks in our brittle solids and how they result in them breaking much easier. So now we're going to speak a little bit about our stress strain graph for polymeric solids. So this is our plastics, our rubbers, and if you remember when we spoke last time, you had to think of it as being like a plate of spaghetti, and the initial stretch untangles the spaghetti, and then that next stretch will stretch the bonds themselves, okay? So when we're looking at a stress strain graph for these types of materials, it looks very different, okay? So a crude type of graph has a Bay and Hooke's law there, but just detangling the chains of spaghetti. And then much more stress is needed to continue that extension because now you are stretching the bonds, right? And of course, we know that when we let go, as long as we haven't reached that elastic limit, it will still go back to the original form. Now that's a very crude version of it. The more realistic one that you will need to regurgitate on your exam looks like this. It's a bit more of a curve to it. Right, so here is disentangling the chains, and at this point here, they are now not tangled anymore. And now I'm starting to stretch the bonds up to this point here. But then if I let go, it doesn't follow exactly the same path back to go to the original form. And why is that, right? Well, think about it. If you keep doing that to an elastic band, I'm sure you've done it and you will have felt it actually gives out energy in the form of heat. So by disentangling those chains and then stretching those bonds, you are actually losing energy in the form of heat. We know that energy is the area under the graph, which is why we have to have this discrepancy here in area. Okay, now this diagram here is called an hysteresis loop, and it explains why there's energy lost due to heat when you extend and put back to normal a rubber band, for example. And you're going to need to regurgitate that in your own words, right? It shows the rubber being stretched from O to A to B, and then released from B to C back to O. The graph is a similar shape while being stretched and being released, right? The curve is very similar, but the extensions are greater while it's being released. The straightened chains do not move back easily into place. They've got to get back tangled up in the same form. However, the release graph does go back to the origin eventually, as the cross links in the rubber remember, they don't have a memory, the original positions of the chain molecules and pull them back into place. This delayed action return of rubber is called hysteresis. And this graph here is called an hysteresis loop. Okay? And the gap here between the two lines is the energy lost due to heat. Area OABDO shows the work you do stretching the rubber. The other area is the energy given out when the rubber is released. And that difference in energy is the heat coming from the rubber. Okay? Basically, this. Loading means we're applying the stretch, the stress, the tension, however you want to call it. Unloading means we've let it go, and now all those molecules are going back to its original form. This area here is the area, the energy, lost due to heat. And that's what you would need to reproduce on an exam. And that's it. That's this unit done. That's the theory of this unit done. Obviously, we've got a lot of practice to do on the exam questions and that, but we've got plenty of time, and we will. I think that's the last thing. Yeah, I'm not overly fussed about the rest of the stuff in your packet, and I'm not going to ask you to do those questions. What I am going to suggest you look at is the very, very back page. If you do ever come back to school and we do practicals, a very common practical is to find the Young's modulus for a metal, right? And you do need to know how to do it. It did get asked one year in an exam. Write down how you would, in a laboratory, find the Young's modulus for a metal, right? So I'm not going to read that for you. That can be your own work. You can read through how to do that. Obviously, you're going to have the length, measure the extension, know the weight applied, etc., etc. Put it all into the equation FL over A delta L, and then that's how you determine the Young's modulus, right? So you're going to need to know basically this bottom diagram here. That's how you would do it in the lab with Daki. And if you come back, we will. But what I would like to draw your attention to before we call it quits is the next part of your homework, which I'll give you a week. But like last week, I want to attempt it, photo it, and upload it. Okay, I have to have something from you to input into my engagement and tracking spreadsheet. Right. So homework 3, there is an hysteresis loop, right, drawn very crudely with straight lines. How much work is done in stretching the rubber from O to B? So that is finding the area under the graph from O to B. So it looks like we have a triangle there and a trapezium there. Work it out. Work out the area under the graph. Answers in joules. How much work is done in stretching the rubber from B to E? So that's there to there and then back down to there. Okay? So I want to find this area here. Find this area here. I can subtract it from what I worked out earlier, and that will give me the work done in stretching the rubber from B to E. Sorry, C. That's a misprint. Change that to C, please, everyone. How much work is done in stretching the rubber from B to C, area under this trapezium here? Apologies, which is why you'll have to watch a video again later. That's a misprint. B to C. Answers in joules. It's energy. What's happening to the rubber molecules in part A and part B? So part A, you're untangling the long chains of spaghetti. Part B, you're actually then stretching those bonds. My phone always goes off in your lessons. How much energy is gained by the rubber over the course of one complete cycle? And what effect does it have on the rubber, right? So work out the area under the stretching graph, OABC, work out that area. Work out the area under the release graph, CDEO, find the difference, and that's the energy lost due to heat. Okay, right. Number 4, if a brittle material such as glass was investigated and you drew a forced extension graph, how would the graph be different to the hysteresis loop? Well, it's just going to be a straight line. It follows Hooke's law, then it snaps. Simple. Right, so I want a little explanation of that. And then the last, no, it's not the last question. There's still plenty of questions. Why is the tensile stress for very thin glass considerably higher than for thicker strands of glass? And that's all to do with the amount of dislocations and cracks, right? If it's much thinner, it'll have a lot less cracks and dislocations. So there's less opportunity for it to break. I just gave you the answer. On to homework number 4, question number 6. Two materials, A and B, right? So there's material A, so that looks like it's a crystalline solid. The base Hooke's law yields a bit, breaks there. Plot, oh, I just gave you the answer there, right? But it's ductile. Material B, if it's brittle, it's going to be a straight line graph, isn't it? And just come to a breaking point. So plot that and draw it. Fill out those points for A. That's not difficult. Then what we have to do there, use the graph to find the value of the Young's modulus, right? So just, it's a straight line, so pick two nice easy points. Young's modulus is stress over strain. You can work that out. Part B, you're going to have to use the force at which is expected to break. So we're looking at this value here, right? So we've got the extension, we've got this Young's modulus we've just worked out. We know the length of it because it gives us it there, 12, and we know the cross-sectional area. So rearrange the formula E equals FL over A delta L to get F equals, plug in the numbers. Don't forget the units of that will be newtons because it's a force. I think I've given you enough there. And then dislocation question. So just like I spoke about earlier, draw the two lattices and show how that dislocation moves over to stick out on the end. And that's how we get plastic deformation. This one here. Standard crystalline ductile solid. Draw a line in the graph showing what would have happened if the load had been gradually reduced to 0 after reaching about 90%. So that's where your dotted line down there comes in, and you're going to explain you'll have that plastic deformation because you've gone past the yield point. And bizarrely, the next question does it for you. That's exactly what you had to produce on that question there, right? Now, that was tough, and my throat is sore, so I'm going to stop talking. Yes, please. Thank you, sir. That was a long hour, right? And you've done really well to stick with me. If you have, for all I know, you're all down the pub somewhere. Have a go at the questions. You are going to have to dip in and out of the recording of this lesson because a lot of it was tough. Yes, please. Sir.
Coffee or tea?
Coffee, please. Thank you very much. If you have any questions, email me. I will get back to you as soon as I can. Have a good go. I've also put in the pack the unit test for this module. Have a look at it. Obviously, you're going to be asked to do it next week. I'm going to give us all a window, but we're all going to try and do it at the same time. But I now need a rest, so I'm going to say goodbye. I hope you're all well. Take care. Get in touch if you've got questions. Have a break now before you come back to this because it's been a lot of screen time. And I will see you next week. Anybody got anything to say?
Thank you.
I was tough, wasn't it, Al?
Yeah.
Oh, I feel so bad.
Thank you.
You're very, very welcome. Have a good go.
You're all doing really well, I must say.
Yeah, you really are.
Right.
It's so hard to do this at the computer screen, not in the classroom. But hang in there.
That looks hard, sir.
It's really...
What's that? Someone just doodled all over your screen.
Yeah, someone has just done a doodle, yes. All right. Right, hang in there, all right? I will speak to you all soon. Good luck with having a go at the questions, and please take a photo and send them to me.
Bye.
Sayonara. Bye-bye.
Lovely kids you got there, haven't you? You know? Hey, that was good, though. Just listening.
Oh, it's so dry.
Oh,
so hard. This is the worst topic of the entire A-level unit. To do it on a computer screen.
No, just put the date now.
Is he all right?
Yeah.